Let's introduce the segment tree with the range sum query problem. Given an integer array, we want to support two types of operations. First, return the sum of a given range. Second, update the value at the given index. Obviously, the brute force approach is to add the values one by one. Now let's look at how segment trees can speed it up. Segment tree is a special binary tree. Every node stores the pre-computed sum of a range. The root node covers the entire array. The left child covers the left half of its parent, and the right child covers the right half. Left and right children are recursively defined. At the bottom, a leaf node cover only one element of the array. So how does this help? Now for range queries, we can answer them by combining pre-computed segments from the tree. This brings down the time complexity to O log n. To implement a segment tree, there are two options: a tree-based approach and an array-based approach. Personally, I think the tree-based approach is easier to understand and has less detail to memorize. So, for the rest of this video, we'll use a tree-based approach. Now, let's look at how to build a segment tree from the array. The build process is done recursively. The function takes two integers specifying the range, L and R, and returns a node object covering this range. The process starts with the root node that covers the entire array. In each function call, we first calculate the midpoint of the range, and then recursively build the left and right child. And after many splits, the range becomes just one element. This is the base case for the recursion. Because this node represents the sum of one element, its value is set to that element. After both children are built, we set the sum value at this node as the sum of its children. For the right half, let's look at how the code runs. Next, let's look at how range query works. Let's revisit one example we saw earlier. There are two types of highlighted nodes. Nodes that are completely within the query range are highlighted to orange color. The sum value at these nodes are included in the query result. The second type of node is highlighted with a lighter orange color. These nodes are partially in the query range. They function as intermediate steps, passing down the query to a descendant that's completely in the query range, and collecting the result. For these partially in range nodes, we first calculate the midpoint of that node, and then forward the query to both children. Notice that it's possible that children are completely out of the query range. In this case, we just return 0. The last topic in this video is how to do single value updates. Similar to range query, we start from the root node, calculate node midpoint, and recursively pass down update operation to left or right child. Eventually, we'll come to the leaf node for the given index and update the value. After child recursion returns, the parent node is recalculated by combining children sums. All ancestors of that leaf node will be updated, up to the root node. Let's look at another example. Finally, we will analyze the time and space complexity for these operations. Before we start, it's helpful to figure out two values: the height of the tree and the total number of nodes in the tree. The height is log n. This is because at each level, we split the range into half. We can split at most log n times. Total number of nodes can be upper bounded by a full binary tree, which has two n-1 nodes. For constructing the segment tree, each node takes constant time to create. So time complexity is O(n). For range query, we have two observations. At each level, there can be at most two nodes that are partially in range, intersecting with left and right bound respectively. So the total number of partially in range nodes is at most 2 log n. The second observation is, each partially in range node has at most one child that's out of range, and at most one child that's fully in range. So the total number of visited nodes is linear to log n. For single value update, only one node will be updated at each level. So time complexity is also log n. Finally, the space complexity is O(n) from the total number of nodes.